In this video, we are going to talk about integrations involving hyperbolic functions. Now, evaluate integral of dx over x square root of 1 plus x squared. So how do we evaluate this integral? Remember that from hyperbolic identities, 1 plus cosec squared x is equal to cot squared x. So what we will do is that we are going to make a substitution such that we would put cosec squared x here, such that we can reduce all of the square root into cot squared x. So now what we will do is that we will say let x to be equal to cosec a. So x squared, half. Now this half is very important. It is important because there is a 4 here, so that when we square x, we will get divided by 4 and this 4 will go away. So x squared is equal to 1 over 4 cosec squared a. So what is the x? The x is equal to half of, if you differentiate cosec a, you are going to get minus cosec a cot a dA. This integral of dx over x root 1 plus 4x squared becomes integral of dx is half, then times minus cosec a cot a dA divided by, then x is half cosec a, and then square root of 1 plus 4 times 1 over 4, then x squared is 1 over 4 cosec squared a. So here's cosec squared a. So this half and this half will cancel. Cosec a and cosec a will cancel. So the integral becomes integral of, so let me pull this minus out. So it becomes cot a dA divided by square root of 1 plus this 4 and this 4 will cancel. So it will be left with 1 plus cosec squared a. So this is equal to integral of cot a dA divided by cot a. So the integral becomes integral of dA, and if you integrate dA, you are going to get a plus c, which is the constant of integration. However, we said that x is equal to half of cosec. We said x is equal to half of cosec a. So this implies that a is equal to cosec inverse of 2x. So therefore, the integral of dx divided by x square root of 1 plus 4x squared is equal to a, which is cosec inverse of 2x plus c. I would like to write this as cosec inverse of absolute value of 2x plus c. Evaluate integral of dx divided by square root of 9x squared minus 25. So what we will do is that, remember that from hyperbolic identities, cos squared x minus hyperbolic sine squared x is equal to 1. So hyperbolic sine squared x is equal to hyperbolic cos squared x minus 1. So you can see that this looks in this form. So what we will do is that we are going to say that we should let x to be equal to, now you see that when we square 3 it is 9, and when we square 5 is 25. So what we will do is that we will let x to be equal to 5 over 3 cos A, such that when we square x, we are going to get 25 over 9 cos squared A. So that when we put all of this here, we can factorize the 25 out, and we'll be left with cos squared A minus 1. And then we can then use this hyperbolic identity. So the integral becomes, however, let's find dx. Dx is equal to 5 over 3. Then if you differentiate cos A, you are going to get hyperbolic sine A dA. And therefore, the integral becomes integral of, now, dx is 5 over 3. Sorry, let me write the integral well. Dx is 5 over 3 hyperbolic sine of A dA divided by the square root of, now, here is 9 times x squared, but x squared is 25 over 9 cos squared A. So here is 25 divided by 9 cos squared A, then minus 25. So let me continue from here. Now I want to pull out 5 over 3 because it is a constant. So if I pull out 5 over 3, we'll be left with 5 over 3, then integral of sin A dA, then divided by, now this 9 and this 9 will cancel out, so we'll be left with square root of 25 cos squared A minus 25. So this is equal to 5 over 3, then integral of hyperbolic sine A dA divided by, now I want to factorize 25 out of the square root. If I factorize 25 out and I take square root of 25, I'll get 5. So here will be 5 times the square root of cos squared A. Remember, I factorized 25, so here will be left with minus 1. So I can bring that 5 out, and this 5 will cancel this 5. So we'll be left with 1 over 3 integral of hyperbolic sine A dA divided by, we said that sin squared x is equal to cos squared x minus 1. So all of this will be cos squared A, sorry, sin squared A. But square root will cancel the square, and therefore you'll be left with hyperbolic sine A. So this hyperbolic sine A will cancel this one. So the integral becomes 1 over 3 integral of dA, and that is equal to 1 over 3 A plus the constant of integration C. Nonetheless, we said that x is equal to 5 over 3 cos A. So it implies that A is cos inverse of 3x over 5. And therefore, this becomes 1 over 3 cos inverse of 3x over 5 plus C. Evaluate integral of dx divided by square root of 1 minus exponent 2x. So what we will do is that let's let x to be equal to natural log of absolute value of sec A. Now you will get the reason why I am doing this substitution soon. So having done the substitution, then what is dx? First we differentiate sec A. If we differentiate sec A, you are going to get minus sec A, then tan A dA. But because there is a natural log here, we need to divide everything by sec A. So dx is equal to this sec A and this sec A will cancel out. So that will be minus hyperbolic tan A dA. So the integral becomes integral of dx, which is minus hyperbolic tan A dA, divided by square root of 1 minus exponent. Now 2 times x, and x is ln absolute value of sec A. So now proceeding further, I'm pulling out the minus sign. So minus integral of hyperbolic tan A dA, then divided by minus 1 minus exponent. I want to bring the 2 here, so it becomes natural log of sec, absolute value of sec squared A. But exponent ln is 1, so this becomes minus integral of hyperbolic tan A dA, divided by 1 minus sec squared A. Sorry, but there is a square root here. I forgot of the square root. There's a square root here. Now, from hyperbolic identities, we know that 1 minus sec squared A is equal to hyperbolic tan squared A. So therefore, 1 minus sec squared, square root of 1 minus sec squared A will be tan A. So the integral becomes minus integral of hyperbolic tan A dA, divided by square root of 1 minus, minus integral of hyperbolic tan A dA, divided by tan A dA. So at the end of the day, it becomes minus integral of dA, and that is equal to minus A plus C. Nonetheless, we said that x is equal to ln sec A. So let me evaluate it here. X is equal to natural log of absolute value of sec A. So it implies that exponent x is equal to sec A. So A is equal to sec inverse of exponent x, and therefore this becomes sec the integral, which is integral of dx, divided by square root of 1 minus exponent 2x is equal to sec hyperbolic sec inverse of exponent x plus c. Evaluate integral of hyperbolic tan of 2x dx. So now hyperbolic tan of 2x dx can be written as integral of hyperbolic sine of 2x dx, divided by hyperbolic cos of 2x. So let's let A to be equal to cos 2x. Now the A is equal to 2 hyperbolic sine of 2x dx. So making dx the subject, it implies that dx is equal to dA over 2 hyperbolic sine of 2x. So the integral, which is integral of hyperbolic tan of 2x, is equal to integral of sine 2x, sine 2x, then divided by cos 2x, but cos 2x is now a, so divided by a, then dx is dA over 2 hyperbolic sine of 2x. So you see that this one and this can cancel out, so we'll be left with, now there's 1 over 2 here, so let me pull it out, half of integral of dA over a, and this integral is equal to half of ln absolute value of a plus c. But we said that a is equal to cos 2x, and therefore this is half of natural log of absolute value of cos 2x plus c. There is another one too here, which is to evaluate the integral of square root of tan x sec squared x dx. So let's let a to be equal to tan x. So dA is equal to, if you differentiate hyperbolic tan x, you get a hyperbolic sec squared x. Square root of tan x becomes square root of a. Sorry, there is a dx here. And then times sec squared x. So sec squared x. But dx is equal to dA divided by sec squared x. So this becomes integral of square root of a, then times this sec squared x and sec squared x will cancel out. So square root of a dA. And now let me rewrite this as integral of a exponent half dA. So when you add 1 to half, you will get 3 over 2. So you are going to get a exponent 3 over 2 divided by 3 over 2, then plus c. And then in rewriting this to be 2 over 3 a exponent 3 over 2 plus c. But we said a is equal to tan x, so this is 2 over 3 tan hyperbolic tan of 3 over 2 x plus c. Now a tan 3 over 2 is the same as square root of tan q. So this is 2 over 3 square root of the hyperbolic tan q of x plus c. So we are supposed to evaluate tan squared x dx. So this can be written as integral of tan squared x dx is the same as hyperbolic sine squared x dx divided by hyperbolic cos squared x. But then we know that cos squared x minus hyperbolic sine squared x is equal to 1. So this implies that hyperbolic sine squared x is equal to hyperbolic cos squared x minus 1. So we can replace the numerator with hyperbolic cos squared x minus 1, and therefore the integral becomes cos squared x minus 1 divided by cos squared x and dx. So let's break the integral into 2. In breaking the integral into 2, it becomes integral of cos squared x divided by cos squared x, then minus integral of 1 divided by cos squared x. Sorry, there's a dx here. So this becomes, this cos squared x and cos squared x can cancel out. So you are left with integral of dx, then minus integral of 1 divided by cos squared x dx. So this is equal to integral of dx minus integral of sec hyperbolic sec squared x dx. If you integrate dx, you are going to get x minus. Now, if you differentiate tan x, you are going to get sec squared x, that is d dx of tan x sec squared x. So if you integrate sec squared x, you are going to get tan x, so minus hyperbolic tan x plus c. Integrate tan x sec cube x dx from ln 2 to ln 3. Okay, so let's rewrite this function as integral of tan x sec x in one bracket multiplied by sec squared x dx. Then we are doing the integration from ln 2 to ln 3. Then now, what we will do is that let's let a to be equal to sec x. So dA is equal to, if you differentiate sec x, you are going to get minus hyperbolic tan x and then sec x dx. So this implies that dx is equal to minus dA divided by hyperbolic tan x, sec x dx. There's no more dx here, so sec x. But then we are doing, this is a definite integral. So since we have let a to be equal to sec x, we need to change the limit in terms of a. So now if x is equal to natural log of 2, what is a? Remember that we said that a is equal to sec x. Now this sec x can be written as 2 divided by exponent x plus exponent minus x. So a is equal to 2 divided by exponent natural log of 2, then plus exponent natural log of minus natural log of 2. So a is equal to 2 divided by exponent natural log of 2 plus exponent natural log of 2 exponent minus 1. Now exponent ln is 1, so therefore a is equal to 2 divided by 2 plus 2 exponent minus 1 is the same as 1 over 2. And then this is equal to 4 over 5. So we need to do the same for ln 3. So if x is equal to natural log of 3, now this 4 over 5 is the same as 0.8. So if x is equal to natural log of 3, then a is equal to 2 divided by exponent ln 3, then plus exponent minus ln 3. If you do this, we are going to get x divided by 10, which is the same as 0.6. So this integral becomes integral of tan hyperbolic tan x sec x. Then now we said a is sec x, so sec squared x is a squared, then times dx, but we said that dx is minus dA divided by hyperbolic tan x sec x. So here is hyperbolic tan x sec x. So that and that will cancel out. However, there is something that we missed. Remember that the integral is from ln 2 to ln 3, and then we got ln 2. When x is equal to ln 2, a is equal to 0.8. And when x is equal to ln 3, a is equal to 0.6. So we need to show the limit there. So the integral becomes minus integral of 0.8 to 0.6 of a squared dA. But because we always integrate from the lower limit to the upper limit, 0.8 is greater than 0.6. So what we'll do is that we'll kill this minus. So we can use this minus to swap the limit. So this becomes integral 0.6 to 0.8 of a squared dA. And that is equal to 1 over 3 a exponent 3 evaluated at 0.6 to 0.8. So this is equal to 1 over 3 open bracket 0.8 cube minus 0.6 cube. And when you evaluate that, we are going to get 0.0987.